happy to introduce for you our last speaker of this PhD seminar series by Zoom. In fact, the entire series in any case. It's Edmond CHAN, who is a first-year student, and he will introduce his team. And he'll be speaking to us about magnetic, magnetic and structural chiralities in manganese, antimony, oxygen. Okay, please begin, Edmond.
Yeah, thank you, Henry, for the introduction. So I'm Edmond CHAN, a first-year PhD student, and I'm supervised by Navid Qureshi from the ILL and Chris Stock from the University of Edinburgh. And today I'm going to present my PhD project. So as an overview, let me introduce you to the subject, give you a state of the art of the compound. Then I will show you some results and give you a conclusion and an outlook of what I have done so far. So my PhD project relates to the topic of multiferroism. So a material is said to be multiferroic when it has two or more primary ferroic moments. And these materials are very interesting. For example, you can have material in which you can interact with the magnetic moment with the electric field and vice versa. And now this multiferroic term is mostly used to refer to these magneto-electric multiferroic materials, and the definition has been extended to all kinds of magnetic order, such as antiferromagnetism and ferrimagnetism. So these materials provide a lot of novel applications for signal generations, sensors, and information storage. And it's also challenging in terms of physics because you often find a very complex magnetic structures and different symmetries from the ferroic orders. But today we have a lot of complementary techniques that we can use to study these materials, especially in large-scale facilities where you can find neutrons, X-rays, or terahertz spectroscopy. That is one reason why this field is intensively researched today. So now let me give you an introduction to magnetic structures. So if you consider the magnetic moment of an atom J at lattice vector RL, you can describe this moment with a Fourier decomposition. So you do sum over the propagation vectors, which describe the periodicity of the magnetic cells of the Fourier coefficients, which are giving the directions of the magnetic moment, and an exponential term. And in a simple case, you can have only one propagation vector. And if you consider only one atom, you can describe its moments by this formula. And in the simplest case, you can describe a ferromagnetic material by zero propagation vector, which is equal to 0. In this case, the periodicity of the magnetic cells is the same as the periodicity of the nuclear cells, which is shown in black here. Then, if you have a propagation vector of 1/2 along the x-axis, so along this axis, you can have an antiferromagnet, and you can see that the periodicity of the magnetic cells is 2 times higher than the nuclear one. Then, if the propagation vector is also 1/2 over the y-axis, you can also find this periodicity along this axis. And you can have also more complex structures. For example, if you can have a helical structure where the moments are rotating in a plane which is perpendicular to the propagation vector. So the propagation vector is still along the x-axis here. And you can have cycloidal order where the moments are rotating in a plane which contains the propagation vector. Now, let me introduce you the compound I'm working on. So it is MnSb2O6. This compound is crystallizing in trigonal p3-1 space group. So you can see the unit cell of this compound here. It is non-centrosymmetric and it doesn't contain improper rotation as element of symmetry. Thus, if you apply an inversion operation on this structure, you get a non-equivalent chiral structure. So if you think if you look on the C vertical axis, you can think about the structural chirality as the helical winding of the manganese, oxygen, oxygen, manganese super exchange path within manganese triangle. And in this case, the winding is following the left-handed rule. And in the other case, the winding is following the right-handed rule. So this defines the structural chirality of our crystal. Then concerning the magnetic structure, here in the figure are only shown the magnetic ions, which are the manganese ions. So they form some triangles with high spin 5½ and an orbital moment of 0. And the magnetic order starts below a Néel temperature of 12.5 Kelvin. And the moments are orders like cycloid in the AC plane, so AC plane, and the propagation vector is contained in this plane, so it's along the C-axis. Now we can describe the moment of Mn atom by this formula, but what is interesting here is the angle theta, which is describing the angle in the AC plane with respect to the A-axis. And this angle is containing very important information in our system because it contains the magnetic chiralities. So in general, you can define a magnetic chirality as the rotation of the spins with respect to our oriented axis. So in our case, we can define the cycloidal chirality, which is describing how the spins are rotating along the C-axis. So in this case, this chirality is equal to 1. And if the spin is rotating in the other way, it will be -1. Then we can describe how the spins are rotating within manganese triangle. So this is the triangular chirality and is equal to +1 in this case and -1 if the spins are rotating in the other way. So then we can describe this magnetic structure by a Heisenberg Hamiltonian. So in this case, the spins at site I and J are related by a symmetric exchange interaction. So this was described in a previous paper, and they proposed 7 exchange interactions. So G1 and G2 are interplane interactions. G4, it's a straight interplane, sorry, I said intraplane and interplane interaction. Then we can define G3 and G6, which are right-handed interaction, and G5 and G7, which are left-handed interactions. And the values of these exchange constants were calculated by DFT previously. And what is interesting here is the fact that there's right and left-handed interactions are related to the exchange path. And if you invert the structural chirality of the sample, these interactions are actually inverted. So now to sum up, we can label a structural and magnetic configuration of our system by sigma, which is the structural chirality, so left or right, and then the cycloidal and the triangular chirality. So if we look at the Heisenberg energy and that we minimize it, we find that there is a condition on this chiralities, and this only allow 4 different states in our system. Then we know that the cycloidal order is breaking the threefold symmetry from the paramagnetic P321 group. So the moments are ordering within the same plane and not following the directions provided by the threefold symmetry. In this case, we are expecting some threefold magnetic domains to appear in which the plane of rotation of the spins are related by the threefold symmetry. Then a very interesting property of this material, which was predicted in the paper of Johnson in 2013, is that considering that generally in some cycloidal magnetic structure, you can find an electric polarization, which is along the basal moment of the cycloid. And as in this sample, you have the threefold domain, you can actually find 3 directions of the electric polarization in the sample. So if you apply an electric field along one direction, you can actually select one of these 3 domains. And if you apply the electric field in the reverse direction, you are actually switching from one domain to 2 domains. And this can be very useful for some applications. Now we can compare this compound with iron langasite, which is a compound which was very studied this last years. So this compound is very similar because here you have some iron atoms which are forming also triangles, but the magnetic ordering is helix along the AB plane, and the propagation vector is still along the C axis. And in this compound, it has been found that there was a unique structural domain which is imposing the super exchange path. And by describing single ion anisotropy, this select a unique magnetic configuration. And this is very interesting because in most of the rotating magnetic structures, you need an antisymmetric exchange to stabilize the magnetic structure. And this has been shown to be not predominant in this compound. So now we want to know why in MnSb2O6 we have a cycloidal magnetic structure which is actually favored over the helical structure. So this can be done by studying the magnetostructural effect by neutron powder diffraction. Then it has been shown previously that there is a mixture of chirostructural domains in MnSb2O6. So 80% of left and 20% of right structure. So we want to study the link of this structural chirality and the magnetic chiralities. This can be done by Schwinger scattering and spherical neutron polarimetry. And to finish, we can check the accuracy of the Heisenberg model by using inelastic neutron scattering. So now I will start by neutron powder diffraction. So basically in neutron powder diffraction, we are scanning the intensity over the scattering angle, and we obtain a diffraction pattern, and we can refine the positions, intensity, and shape of the Bragg reflections with the Rietveld refinement to extract some structural and magnetic parameters of our sample. So this is a diffraction pattern for MnSb2O6 at T equals to 2.7 K. And the first line are indicating the nuclear phase, and the second green line are indicating the Bragg peak position of the magnetic phase. So before the start of my PhD, powder diffraction was performed at B21 at NIST. So 21 temperatures were measured from 2.7 K to 300 K, including 7 measurements below Tn. The propagation vector was found to be the same as the previous study, and transition temperatures was found between 12 and 13 K. Here you can see how the amplitude of the magnetic moment is evolving as a function of the temperature, and the red line is indicating the transition temperature. Then, if we focus on the evolution of the lattice volume, we can see a very sharp evolution below Tn. And if we look at higher temperature, we can extrapolate the variation of the volume as linear thermal expansion in 3 different regions. Then, so for now, the refinement was done using the P321 space group symmetry. So in this case, the manganese atoms are actually related by threefold symmetry. So we are actually only refining the positions of one atom. So we can try to reduce the symmetry, for example, in C2 space group, which is a subgroup of P321. And this adds actually a degree of freedom for the Mn position, because here we will have 2 unequivalent Mn atoms that we can refine the position. So this allows us to study the eventual evolution of distances and angles within Mn triangle. So there are the results. So you can see that below the Tn, the angles are from one side decreasing and the other side increasing. And this is obviously linked to the evolution of the distances between the manganese atoms. So this can be summarized in this picture. So it seems that the length between these 2 atoms is increasing, and the length between these 2, these 2 distances are decreasing. So in order to confirm these results, we wanted to have a higher resolution measurements. So we made an easy proposal on D2B, and 8 temperatures from 2K to 14 kelvins were measured on February. So we can compare, so in blue, what we have found on B21, and in yellow, the refinement from the data of D2B. And in this case, we have observed no variation of the angles and neither of the distances. But if we look at the value of the angle at above the transition temperature, we can see that it is not equal to 60 degrees as expected in a P321 space group, because the triangle, the Mn triangle, should be equilateral. And in absence of higher temperature measurement on D2B, it's hard to extrapolate how the values will be at higher temperature. And then I have made the refinement in C2 space group. So only 2 unequivalent Mn atom positions were refined. And I also made some trials in P1 symmetry, but I couldn't get any converging fit. So in order to close the structural investigations, we got 5 days beam time on D9 to make some single crystal measurement. So now we will focus on the structural and magnetic chiralities. So first, let me introduce you, explain you what is a twin in crystallography. So if you consider a unit cell without its content, you can see it as the building brick of the crystal. And if this unit cells has a higher symmetry than its contents, that's to say the crystal space group, you can have some twinning. So let's take an example. If you consider this brick that is flat on the bottom and has this indication on the top, you can to build a crystal, you can stick them the same way, like in this image, or you can invert the brick and stick them with an inverted brick. And in this case, you have a mixture of the 2 twins. In our sample, as it is non-central symmetric, we have an inversion twin. And obviously, this inversion is actually switching the structural chirality from left to right. Also, we can have a 2-fold symmetry twin. So in this case, the unit cell is rotated along the z-axis by a 2-fold symmetry. And in this case, the structural chirality is not changed. So in order to detect these structural twins, we need Schwinger scattering. So I will explain you how this works. So if you consider an experiment where the neutron is scattered on a crystal in the reference frame of the neutron, it sees the crystal field of the crystal as moving. So this product magnetic fields which couples to the spin of the neutron, and this produce neutron spin orbit contribution to the scattering, which can be described by this equation here. But what is important in this term is that it depends on the polarization of the incoming neutron. So if you measure the flipping ratio, so the intensity of neutron polarized along a positive z-axis and in the negative z-axis, you can find out different flipping ratio for the different structural twins. Because, for example, this interference terms is actually changing sign by inversion of the crystal field. So if you have an inversion twin, the ratio here will be inverted. And one thing which is very important is that you can only measure that in the case of non-central symmetric crystal, because the electric field will be equal to 0 in the opposite case. And you also need polarized neutrons, else you won't have these terms and you will always measure a flipping ratio of 1. So we have made some measurement on D3. So this was also before the start of my PhD. So in MnSb2O6, you can have 4 twins, and the flipping ratios were measured for 9 reflection. So the values are shown in this figure. Then you will have 4 different values for the 4 different twins. So we have to fit the observed data to a linear combination of these 4 values. So this was done simply by doing a linear combination of these ratios. So the results are summarized in this table. What we can see that the standard error is quite high in these 2 populations, and we have also found some correlations between the populations. So one idea to improve this fit is to add some constraint. And if we actually calculate the magnetic structure factor of these twins, we can see that for the first and the third twin, we get the same magnetic structure factor, whereas it is different for the 2 other twins. So we can generally measure the magnetic structure factor with unpolarized neutrons, but this was not done during our experiment. But from the previous studies, they have observed a proportion of 80% of these magnetic factors and 20% of the other, but they automatically attribute one of the structure factor to the left structural chirality and the other one to the other structural chirality. So they didn't consider the second and the third twins. So in reality, it might be more complicated. So now let me explain you what is spherical neutron polarimetry. So this is a technique which is used to determine complex magnetic structure and chiral domains. And this is what is interesting us in this study. So if you think about the final polarization of a neutron as a function of the initial polarization here, you can get it from a rotational part and created or annihilated polarization. Then you can measure the final polarization along one direction by making the difference of the cross section of the neutrons polarized along one or the other sense of the direction. And if you do that for the 3 directions of the final polarization and for the 3 directions of the initial polarization, you get a 3 times 3 polarization matrix, which is shown here in the case of a pure magnetic reflection. So what is interesting here is the first column, where you can find information about the magnetic chirality in the sample. So this is a picture of cryopad, which is the setup used in D3. So you can find the sample in the middle of two Messenger shields, which are avoiding any external magnetic field. Then the neutrons are incoming in this guide field. So you can see in this video from Navid that how this works. So the neutrons are coming this way in the guide field, and then the nutator is selecting one direction so that the initial polarization here is along the x-axis. Then it's scattered on the single crystal, and then you have the coil and then the output nutator, so that at the end the polarization is analyzed along the y-axis in this case. So if you remember, I talked about threefold magnetic domains, and this is important here because the polarization matrix that we are measuring are depending on the directions of the moments. So if I summarize the aim of the experiment is to determine the proportion of each configuration. So we also know that the polarization matrices are only sensitive to the cycloidal chirality. So at the end, we have only two values of cycloidal chiralities and the threefold domains that we have shown before. So we have at most 6 different polarization matrices to mix for each magnetic reflection. So these polarization matrices were measured for 5 different reflections. And what we want is to make a linear combination of the 6 different polarization matrices and compare it to the measured one to see if the model is fitting to our experiment. So in this case, the results are shown here. So from the Schwinger scattering, these states shouldn't be existing in our samples. But what we can conclude from these results is that there may be a mixture of the remaining states. So they could be some degenerate states. Then I tried to fit the result to another model. So this model was proposed by Kinoshita in 2016. So in this paper, they have found that the rotation plane of the cycloid was aligned along another axis. And also they found that the rotation plane was actually tilted from the c-axis by an angle plus or minus 18 degrees. So if we consider this tilted domain, that doubles the number of polarization matrices we have to mix. So in this case, we have 12 populations to refine. So the results are shown in this table. And there is one problem we had that we had to fix the population of the states to 0 because the fit was diverging. And if you look at the directions of this population, so this is the sum of the population along the different directions, you can see that maybe these 2 directions are privileged with respect to the first one. So as a conclusion, the SNB data is compatible with the tilted cycloid models, and the Schwinger scattering is revealing the mixture of several structural twins and chiral domains. But the magnetic domains could not be uniquely determined by these experiments because we have some difficulties which arise from the mixture of the structural twins and the magnetic domains. So now let me finish with some inelastic neutron scattering. So a very short introduction to spin waves. So spin waves are collective excitations of the ordered magnetic structure. So if we consider linear spin wave theory, we can think about spin waves are very small fluctuations around the spin ground state S. So they are described by these bosonic operators. So if you take the Heisenberg Hamiltonian and you make a Fourier transform, you get the second order terms in terms of bosonic operators. You can then make a diagonalization of this Hamiltonian and get the relation of dispersion of the spin waves. And then we know that in inelastic neutron scattering, we are measuring a cross section which is proportional to the spin-spin correlation function. And this is a product of a spectral weight and the relation of dispersions. So we can actually compare what is observed to what is calculated here. So again, the experiment was done before the start of my PhD. So it was measured at max at NIST. So here you can see energy slice, which was measured. And so far I have calculated the relation of dispersions using the DFT values of the exchange interactions from Johnson. And if I take the theoretical propagation vector, which is actually minimizing the energy of the Heisenberg Hamiltonian, I get this relation of dispersions. But if I take the experimental propagation vectors, which is different, I get some imaginary values. And we can also see that the scale of the exchange parameters seems to be not the same as what is measured experimentally. So as a global conclusion, the powder diffraction was not conclusive to study the magnetostructural effects. So we need a single crystal experiment. Then our Schwinger scattering data revealed the mixture of structural twins, but we lack of constraint to have a more precise determination of the populations. And we encountered some difficulties to ultimately determine the overall chiralities on SNP due to the presence of the twins and of the magnetic domains. And I'm still investigating on the inelastic neutron scattering data to find out more information about the exchange parameters. And in the future, we already have some inelastic neutron scattering data at higher energy. So I might be working on 2 magnons continuum. Then we have some beam times which are scheduled. So we have some beam time at Myra at FRM2. So this is for the study of magnetic structure in MnSb2O6 as a function of the magnetic field and temperature. And we have also beam time on TASP at PSI to study the magnetic excitations under a magnetic field. So thank you everyone for your attention.
Thank you very much, Edmond. Okay, I have just 1 or 2 questions as we wait for the chat to activate. You reduce the symmetry in your structural refinement to C2 in order to allow slightly different positions for the manganese atoms. Is that right?
Yeah, it's right.
And there are 3 possibilities for their position. I mean, there's 3, in principle, there could be as many as 3 different MN sites. Is that right?
Oh, I mean, the other manganese sites are generated by symmetry. So at the end in C2 symmetry, you are only refining 2 sites.
Okay, so there's 2 different possible MN sites. And
Yeah.
what is the evidence for there being 2 different MN sites? What was the justification for reducing the symmetry?
So the thing is that, so we know that the magnetic ordering is breaking the threefold symmetry, and that the moments are aligned in one plane, and it's not, so it's breaking the threefold symmetry. So we wanted to know if there were some structural changes below the transition temperature, which can explain actually this breaking of the threefold symmetry.
Okay, so you have a magnetic transition.
Yeah.
And your thought is that the magnetic order that you're investigating could induce a structural change
Yeah,
on the
yeah, that's right.
magnetocytes. Okay. And okay. All right. So okay, that was one of my questions.
Okay.
Here we have Irina.
I was wondering, I mean, about the future plans, about the inelastic scattering.
Yeah.
Why should the continuum appear? I mean, was it predicted for the, why is that? Because of the chirality or why?
Oh, sorry, I didn't understand the beginning of the question.
You are saying that about two magnon continuum. So
Oh.
why is that?
So actually, this was not predicted at all. It was just measured. So we have to investigate on it to see why we are measuring this actually.
Okay. Okay.
Yeah.
So you see, like the, I mean, not
I
only
mean,
the
this,
waves, but
this
also
was
the.
already measured in the past. We have the data for this, so we just have to think why we have measured this. It's not in the future plans in terms of experiment.
So, I mean, might be this is because of the kind of frustration or.
Yeah.
Okay.
I mean, yeah.
Okay, thank you.
Yeah, I'm reminded of another question I had, Edmond.
Yeah.
We're waiting for others to come into the chat, perhaps. Is what's your feeling, or what's the conventional wisdom about why you have this discrepancy with the D2B data? And I forget what the other instrument was. Could it be a temperature calibration shift, since you didn't go very high on D2B?
So yeah, we went until 14K on D2B, and maybe I don't think there is a calibration of temperature calibration problem, because if we look at the magnetic moment, we can see that on D2B the last measurements we couldn't see anything. So normally the magnetic transition was before this data point.
Okay, so what was the other instrument again?
B21, NIST.
At NIST, okay.
Yeah.
Okay, so that's a mystery.
Yeah, that's that's why we wanted to continue the investigation on a single crystal to see how it behaves.
Okay.
And how did you determine the structure with the irreducible representations or within the magnetic space groups?
Sorry?
How did you determine the structure within the irreducible representations or within the space groups?
Oh, within the space groups. Oh no, you mean the magnetic?
Yeah.
Okay, no. So with the irreducible representation.
And for, I mean, just a general question, because I'm not an expert, for the chiral structure, do you have like imaginary irreducible representations, or they are real values, or they have the real values?
Well, actually, I didn't make the calculations. So actually the model I was using was the model which was studied before. So I just considered the cycloidal ordering. So actually, yeah, I don't really know.
Okay, no problem.
How do we answer? Yeah, sorry.
And Edmond, I was curious.
Yeah.
Has anyone ever tried to make, is this part of a family of compounds? In other words, could you replace the antimony by bismuth, which is in the same column? For example, are there variations of this compound that you can make through substitution?
Maybe, but yeah, I don't know. I mean, yeah, I haven't read the papers related to other compounds of this kind of family, so I don't know.
I'm not really I'm not an expert in magnetism. I've learned a few things, but my impression is that manganese can be very sensitive. Its magnetic properties can be very sensitive to its environment. and its moment can be induced, etc., by neighboring atoms or crystal electric field, blah, blah, blah. I mean, I don't understand this very well, but that's why I was wondering if you could, if it could be interesting to substitute the antimony for something else.
I mean, yeah, it could be, but I think that for now, what we have to study is more like the interactions with the oxygen atoms, which are surrounding the manganese atoms, because this, I guess, have more impact on our system.
And is the stoichiometry difficult to achieve, or is it variable? Could you make a superoxide or a suboxide? I mean, can you over-oxidize it or under-oxidize it? Probably not, I guess.
Actually, I don't know because I didn't do the synthesis.
Okay, there's still no chats coming up. So how long has this compound been around? How long have people been studying this?
Oh, so this compound has been studied first in 1989. So it was just a powder diffraction on the structure, and then in 2013 we had there was an important paper which was describing this this compound as a multifluoric, and then you had there are 2 or 3 other papers which has been published on this compound, but the main paper was in 2013.
So it's relatively new.
Yeah.
Edmond, let's thank both of our speakers. Thank you very much for giving this last, Edmond and Niels, I guess Niels is still with us, for presenting this last seminar day by Zoom. And I'm glad we had a lot of participants. And I hope to see most of you again next week, Thursday.